Thank you, Noel, and thank you to Aerospace Testing for inviting us to talk to you about flight testing eVTOLs. My name's Dean Moore. I'm a flight test specialist at Vertical Aerospace. I'm a flight test engineer by training. I've got 20 years of experience in flight testing fixed and rotary platforms for the Ministry of Defence, Kinetic, who were one of the sponsors here, and Boeing before joining Vertical Aerospace about 15 months ago, helping to lead our latest program in terms of flight testing. There's been a lot of debate around eVTOLs, advanced air mobility, over this symposium. So I hope that we'll all get a bit of an insight as we look at our journey in flight testing eVTOL aircraft. I'll talk for about 20 minutes, hopefully, and give us some time for some questions at the end. It's like, obviously, there'll be a microphone coming around, so if you raise your hand, myself or Noel will get that microphone to you before you answer the question, so that the folks who are watching at home can listen in and hear us. So in terms of the slide deck, just looking at our journey in making air travel personal, on demand, and zero emissions, I'll talk through the evolution of eVTOL concepts, very much from a biased point of view. From our point of view, as you'll see, we are not wedded to a particular type of concept, and we've gone through a number of iterations of that in flight testing. Talk about some of the technologies we need to prove to make this whole part of the industry a reality, and talk about some of the preparations we've been doing for flight testing and some of the risks that are involved. So just looking at going through, as I said, our mission of making air travel personal, on demand, and carbon free. We've a relatively young company, so we've been going for just over 5 years, and we've achieved quite a bit, which we'll talk through here. Our first, effectively a full-scale prototype, it was V8X1. It's full-scale in that it was designed to have the capacity and volume to take a person remotely flown. That was the concept, with, as you can see, 4 ducted fans at the 4 corners of the aircraft. It was put together fairly quickly by the initial sort of 6 engineers in the business, so it was a rapid prototyping idea, and that was done within 2 years of the company starting work. There were some aspects to this aircraft that proved to be something that we didn't like. We wanted to evolve. So those ducted fans have 1 motor and 1 propeller in them. So in terms of a safety case, sort of reflecting on the international feeling that if one of those motors fails, c'est ne pas bon, c'est fini. So we need more redundancy in that aircraft to allow us to get something certified. So that was one aspect. And the forward speed, those ducted fans didn't tilt. So as you get slightly faster speed, the air tends to trip and separate over the leading edge of that. So that wasn't great for our propellers either. So I say propellers, I should say rotors. I'll probably get told off by my colleagues back at base for that. So that gave us a great insight that actually there was a lot of possibility in doing this, but we needed to make some changes to our concept of how it might look. So then we've come up with X2, which, as you can see, has, and I've got this wrong before, it's got 6 points around the aircraft. There's 2 motors and 2 rotors at each of those points, so there's 12 motors and 12 propellers in each position. We've got rid of the ducting. It's been designed, again, it's full scale, to be remotely flown only, so it's completely automatic, with a reasonable top speed of 50 miles an hour. But a problem we have with that is that's pretty much the top speed. The rotors are starting to feel the strain. It's not going to be very comfortable for our passengers with fixed rotors, because we're going along obviously tilting the aircraft. So it's not comfortable as a ride. And we have fairly limited range in that we're relying on rotors pointing directly up. So in terms of looking at an addressable market, actually there's a bigger market for something that can go further and faster. So this is a bit limiting for us. The other big thing for us, as we will talk on later, is noise. So the rotors at the bottom, as you've probably noticed, they're counter-rotating. The rotors underneath are having to work with the wake of the rotors above. So that is not a good noise situation. It ends up increasing the amount of noise that we're getting off the aircraft, and we need to do a lot better with that. So that's why we've arrived at our latest concept and what we're building right now and preparing for flight testing for, which is VAX4. It still has 4 in the title because it's 4 passengers, but we've talked about the regulatory requirements and the regulatory bar that will have to be set for autonomous flight, and certainly talking about public perception and acceptance of flying around in these vehicles. In the near term, that's only really going to be done with a pilot sat in the front. So this aircraft will carry 5 people, but 4 passengers, hence the X4. And as you see, it's winged, and we'll talk about some of the aspects of the design and structure in a moment, but that winged configuration gives us the extra range, it gives us the extra speed, so we can cover a wider sort of demographic of people who might use it. 4 tilting rotors on the front of the wing, 4 rotors at the back that spin up and spin down, depending on when you need them as you come into the rotor-borne environment. So that's what we're working on and building right now. And in terms of the concept of operations and why we're going that way, we talked about this yesterday in the panel session. We need those aircraft to be extremely safe, more so than an airliner, because of the operating environment they're in. Helicopters do this advanced air mobility role already, but they don't tend to do it that much because they are too noisy. They're quite expensive to buy and to operate. So our big drive is to really push down on the noise envelope of the aircraft so we get that public acceptance and we can get these things flying around, particularly in urban environments, but we also want to slash the cost of ownership from buying to operating as well. And just looking at one of our launch customers, Virgin Atlantic, just an idea of the winged aspect of the aircraft allows them to access a much wider population. Say in the UK, we've got similar models for our friends at American Airlines, one of our other launch customers, around Dallas and New York as well. So that gives us a much bigger addressable market for the aircraft to be sold into. So just then looking at the technologies that we need to prove to make this, I won't touch everything. I'll try and do justice to everything as we're going through. But as you can imagine, there's a whole load of it. I could chat probably for a full day about the various aspects of the aircraft. One of the big things, as we've talked through, and I will touch on it again, is energy storage and distribution. We've got in the vertical regime, or in the rotor-borne regime, an extremely high power demand for a potentially very short period of time. So we're having design to be able to have enough energy that we can access and distribute that to the motors around the aircraft. We also need to make sure that the pilot on board has a very reliable understanding of the energy that they have on board the aircraft, but equally, as everybody knows, as batteries get hot, as we're drawing current out of them and we're working them very hard, the actual ability to draw on the energy that you have stored in that battery goes down as well. So finding a way of providing that information, so good human-machine interface, is a massive challenge. And so that's a massive area for us working on and developing as we go through the process of developing our X4 prototype. And then in structure, as I mentioned, our sort of concept is very much passenger focused. We don't want passengers to have to climb over beams and barriers or duck underneath things or worry about rotors smacking them in the head, those sorts of things. So we need the passengers to be able to get into the aircraft easily, quickly. We want to turn these aircraft around quickly as well. So the high wing is there because it gets the aircraft or the wing well out the way of people. So it's aimed to be there so 6-footers like me can walk straight up to the cabin and get straight in. That aspect and the pylons and where the rotors are, obviously with different speeding rotors as well, or variable speed rotors, gives us an issue of looking at how the vibration is catered for in that structure. And then also, how do we mass produce these aircraft with low-cost carbon manufacturing techniques and making that ride for the passengers we mentioned before. That passenger ride needs to be nice and smooth. If you're being chucked around like you would be in an Apache helicopter, you're probably not going to come back for a second ride. So those are all things that we need to focus on as we're going forward. The motors, as you could well understand, working in a hover and then working in forward flight up to somewhere near 200 miles an hour. The effectiveness of those rotors and designing them to cater for both of those regimes is quite interesting. We've got a 5-bladed rotor on our front rotors at the minute and a 4-bladed on the rear, because we also need to be able to stow those aft rotors as well. So trying to make sure all the figure of merits work across the entire speed range of the aircraft is an interesting challenge. And then flight control. Initially, all these pilots will be pilots who've got a lot of experience, but we are going to, and I think it was addressed yesterday in the urban air mobility briefing we had, there's going to be a lot of these things around. We need to look at how we open up the pool of pilots that can operate this aircraft. There's a concept of simplified vehicle operations. So we're looking at using unified control to make the handling and flying of these aircraft extremely simple. So just as a general overview, the idea is that it doesn't matter what speed you're at or what part of the flight regime or configuration the aircraft is, the inceptors that you operate always in the same sense, no matter what speed you're at. So it becomes very intuitive and easy to fly. That's the plan. It does mean we have a fly-by-wire triplex flight control system, but it's very much not a CS-23 aircraft. It's not a stick with a cable attached to an aileron or a trim tab. So we're just going through all those aspects of harmonizing the control laws and the aircraft as a whole with all the aerodynamic surfaces and vectors from rotors to ailerons to flaperons and ruddervators at the back of the aircraft. And then I'm going to click again and hope the video in the middle starts working. As you'll see, we have single rotor rig at base at the minute, testing out the initial motors and rotors. We've had a full 3-meter diameter rotor on that rig, and it's now being modified for the tilting mechanisms to improve those. Battery testing, huge amount of battery testing. Many have suffered battery fires. Our big thing, as I mentioned earlier, is about thermal runaways and managing the heat in those batteries. You can see in the video, there was a torch there. The only way you start these things going, getting a cell to thermally run away, is to stick a torch on it. So you can see the basic chassis, an early basic chassis of our battery packs there, and slowly but surely, and this is the nice bit, it doesn't go straight away, we've been looking at understanding when one goes, how does that then transfer around the rest of the battery pack? As mentioned yesterday, once these lithium-ion batteries go, they've got all the material they need for the fire triangle to keep going. So we want to avoid this, but equally we want to understand how this works and what the mechanics are. We will be putting effectively a wrapper, a heat-resistant carbon composite wrapper around this, so that if, in the unlikely event this did happen, you have sufficient time to get down to the ground. And in terms of getting down to the ground, we've also been dropping these battery packs from about, I think it's 50 feet, just to make sure that we've got crash worthiness. So if we did crash, those battery packs stay together. And that's been witnessed by EASA and the CAA as well, to make sure that they understand this technology as we're trying to look at how we set the certification rules for it. And then lots of useful normal wind tunnel testing, understanding how the rotors work together with the wing, and as the whole aircraft, looking at sub-components in terms of loads and vibrations. And lab testing, plugging different boxes together to make sure they all start to talk and work together. And then in terms of certification, we've got EASA and the FAA producing lots of paperwork at the minute about what they think. Some of it is harmonized, some of it is not as well harmonized as we would like, and they're working on that, and we are contributing to that conversation. You can see at the top, eVTOL is one of the documents that helps give us a means of compliance for these aircraft. That's a difficult task. I think we all understand that. There are lots of different concepts, and EASA having to try and produce a rule set that covers all of them, all of the concepts that we have touched on as we've gone forward. So it's not an easy job. And as a flight test engineer, one of the areas that I'm particularly excited about is minimum handling qualities. So EASA and the FAA are using a US Army document called ADS 33, and mission task elements within them, which you can see an example of at the top right corner. That is a military requirement. So you would expect that those aircraft are more aggressively operated and flown around. A passenger in the back of an eVTOL would spill their gin and tonic if they were being flown in that manner. So it's about making sure we tailor those mission task elements to be appropriate for the role. The other element for ADS 33 is actually, if you've ever done it, it takes a long time. And as I said earlier, the concept of operations is mostly wing-borne. And you can see an example, a pie chart of how long roughly one of our missions would be in the different phases, mostly wing-borne with a very short period of being rotor-borne. But my cert program, and I'll caveat that the one in the bottom right-hand corner is not exactly what my cert plan looks like right now. It's just an example. It's a 40-40-20 split, just as an example. But the reason I put it up is actually the certification program is going to require a significant amount of time in the rotor-borne environment because we're certifying effectively a helicopter and a fixed-wing plane and something that goes between the two. So we need to work out how we're going to achieve that with an aircraft that's still representative of the end product. And actually, and the FAA are very keen on this and are very open to this. I think we need to work with the EASA a bit more about validating models and using simulation and modeling to help as part of that certification effort in the rotor-borne regime. Otherwise, we'll be here for a decade doing rotor-borne testing to get these aircraft certified. So that's a challenge, and we'll need to work with the regulators on that. And then in terms of flight test preparation, on the right-hand side is just a schematic of the telemetry setup that we're going to have with the aircraft. We've achieved quite a lot in a short period of time, but this aircraft is another step up. As you can imagine, if it's 2 meters to get under the wing, the aircraft now is not small. It's 50-meter wingspan, so it's a big plane. We need to build up that competency within the organisation. People like myself have joined. We've just added a new test pilot as well to the organisation, but we're also enhancing the skill set of the people that are already in the business and actually need to work on how do we become qualified and competent in flight testing the aircraft. And we are going to use our pilot in the loop simulator, which I didn't add in there, which is going to help verify the flight control mechanisms and strategies to help us. I'm going to link that to our telemetry station so we can rehearse those test missions, prepare so that we know what to expect. And for those things that might happen, those failures that could possibly happen, we should hopefully be as prepared as we can be to handle those in the appropriate way. And all that's part of a much wider safety management system and focus. And along that lines is making sure we have a good learning culture and that there are plenty of people who've done experimental aircraft in the past, and we can learn huge lessons from them. Telemetry is a good example. The X-31 crash that NASA had and DLR had is a fantastic YouTube video if you get the chance to do that. So we can learn a lot from what's happened, not just with our own experience, but what others have done. The other part is we need to find the right test location. We're based in the middle of Bristol. We are not going to flight test this aircraft in downtown Bristol. So part of the preparations is to find an appropriate location that can handle the sorts of things we are trying to do and the unfortunate events, the risks, and handle the risks and provide us with the appropriate mitigations for whatever we do. In terms of actual flight test risk, the big one that is interesting for me, there's a lot of investment coming into this area of the industry. A lot of us are startups. So there is a quick, innovative, quite big churn on the way we do stuff. But equally, flight tests are generally quite cautious, progressive, incremental, and trying to balance up going quick, getting stuff done. We've all heard about the very ambitious certification timelines that we're all talking about. I put James Reason's safety space model up because I use it a lot inside Vertical Aerospace because we have to find that right tension. We can't sit here and take 20 years to prove this because we'll all just burn a lot of money and become bankrupt. But we still need to be safe enough. We are going to have to look at our risk appetite and make sure we get that right to progressing the technology. I talked about fire. That's one of the big things we need to worry about, not just when we're flight testing, but also when we are simply charging the aircraft. The number of people who've had battery fires when they've just been charging it. So we need to bear that in mind. We equally also have a lot of people working on an aircraft in and around it when it's going to be in a high voltage state. It's not a 240 volt domestic supply, this aircraft. We're talking hundreds of volts. High voltage systems come with certain safety precautions, and we're going to have that aircraft on the ground for long periods where we could have the risk of injuring people or worse. And equally, actually, if we don't injure people, but we do the wrong thing, we could arc and destroy wiring and have to replace it, which would put us back as well. So we need to be mindful of the electric high voltage hazards on the aircraft. And then just the simple bits of loss of control. Talked about the pilot in the loop simulator. We have a fairly interesting flight control law set up, as you can probably understand from what I've just talked through. We've got to make sure all of those aerodynamic effectors work with the pilot instruments, their inceptors, and how they operate the aircraft. So we need to be mindful and work through in simulation modeling as best we can that we have appropriate control over the aircraft and do that incremental approach in terms of expanding the flight envelope. And other bits that we just need to be I'm mindful of particularly, and again, this comes from learning lessons from the past, where flight test programs with that pressure to push on have perhaps not have looked at the data as it's come off, initial looks and gone, yeah, that's okay, we go to the next step tomorrow, and they might well have missed something. So we need to be mindful that we give ourselves enough time to get the data we have obtained on one day to be reviewed appropriately to make sure we are safe to go to the next step tomorrow. So we need to make sure that we have that, hold that tension to make sure it's the right tension, but not enough that drives us to the point of rushing too quickly. And then equally, we're operating an aircraft at an airfield. We will focus a lot on all the hazards around the specific elements of the technology we're developing, but we're still an aircraft. We're still operating on an airfield. We need to be mindful of other traffic. It's a common flight test risk of being heads in and not seeing that aircraft or glider that's out there. So as well as all the new and novel things, we still have to operate the aircraft to be mindful of those aviating risks. So hopefully I've given you a fairly quick canter through eVTOL concept. Our journey is really interesting because we've kind of touched on lots of the aspects. We've not wedded to one particular concept, and we've gone with what we think will work in terms of a final product. But there's obviously lots of those aircraft configuration concepts out there going out as real products, eHang and Volocopter, for examples. Talked about some of the key kind of technologies we're hoping to prove and are in the process of proving through ground testing. And I think the big thing is, hopefully you'll have picked up, is that actually the big element of flight testing eVTOLs is doing all the ground testing and modeling and simulation beforehand to help prove out that you've got something that will work and you know what you're expecting to see. And then just talked around some of the flight test preparations, setting up the telemetry system in a way that gives us appropriate control over the conduct of the flight. We can monitor everything as we go, but equally using the technology we have to link those things together and practice before we go. So our first flight will not really be a first flight because we'll have done that first flight and many others plenty of times in the simulator with the setup we expect to see in real life. And we talked about some of the main sort of risks around the sort of tension of trying to get certified really quickly, but making sure that we expand our flight envelopes in the appropriate way because this technology is pretty new. We're all learning as we're going along. So we have that tension between going fast and getting something out there and selling aircraft, but doing it in the appropriate way to hopefully keep ourselves safe and also beyond that, the customers that end up operating and flying in the aircraft. And with that, I guess we open up to questions. So if anyone's got any questions, if you pop your hand up and then we'll get a microphone to you at some point. The gentleman, as far away as you could get from where you are. I can speak up if you can hear me. I think it's more a case of making sure that the people at home can listen in. So if I can temper your excitement and keenness.
Hello.
That's lovely.
Hello, this is Kevin McKenzie from a company called TestFux. We primarily test flight actuation systems, power systems, and so on. But I'm interested to know if you are the sole OEM for the aircraft and all of its components, or if you have a supply chain for things like flight control actuators and that sort of thing.
No, I can go into all that kind of stuff. It's not quite flight test, but I'm very happy to talk about it. So I think a big part for the whole business model for Vertical Aerospace, and we very much deviate from someone like Joby Aviation is a good example, who are, to use business terms, they're vertically integrated. They've taken on board all of that themselves. Vertical Aerospace has chosen not to do that. So we have certain areas of excellence that we think are particularly key to this type of aircraft, mainly around the rotors and the batteries. So that's stuff that we're definitely keeping in-house. Avionics is something that, and flight control, as a good example, as you mentioned there, it's something that actually that technology is out there. There are good suppliers out there already that we can use their experience because they've been doing and certifying these sorts of things for many, many years. So we've got a key partnership with Honeywell around flight control systems and displays as well. So a lot of our avionics are Honeywell avionics. And equally, we've just obviously signed up a partnership with Rolls-Royce around electric power units as well. So we're working with hopefully the best in the industry to make sure that we aren't there trying to find out how to do all of this stuff as a startup, but we do look at keeping hold of those key aspects of the aircraft around the rotor and the battery. So composites, we've just signed GKN in the room as well. So we're working with GKN about wing manufacture for the production aircraft, all those sorts of things. So yeah, we're leaning into the supply chain to use the best expertise to drive down the risk of us being able to certify in the sorts of timelines we're talking, because they are still quite, they're all very ambitious for everybody in the industry. So, no, it's a pleasure. Hello, Pete. I don't know if your microphone's on. Is it on?
Yeah, it should be on, but get it closer.
I can't hear you coming through the speaker. Sorry, Pete.
Is that better?
Yeah, that's brilliant. Thank you.
When's first aircraft delivery?
When's the first aircraft delivery? So the ambitious plan we talked through is that they want revenue flights happening from 2025. So that means we're going to be certifying this in and around that sort of time frame. So the aircraft, the prototype aircraft, is well on its way to being manufactured right now. I'm a flight tester, so I'd have loved to have been built already, and I'd love to be standing here saying we've done our first flight. Unfortunately, that's not the case. But yeah, so they're looking at having certified aircraft out there doing revenue delivery flights in 2025. So that's about the sort of time frame we're talking.
So 4 years of flight testing and cert plan then?
Yes.
Effectively.
So I think the interesting kind of aspect for the sort of startup mentality as well, we're already talking about the rotors like I showed you on the screen. I don't think will be the rotors on the final aircraft. I think we're going to see actual almost a spiral development on our initial test aircraft. And then we've already got plans for obviously how we get to a point of doing those initial production aircraft for a certification campaign. So there's clearly a lot of intense work going on about starting and ramping up to answer that requirement to try and get aircraft out there for 2025.
More questions?
Hi, how you doing? Just asking a question, is there a requirement for crash recorders on an aircraft like this? Or is it related to the number of passengers you're using?
That's a really interesting point. I don't know the answers to that one, I have to say, off the top of my head. Normally you would expect that, I'm looking at Jeff and Jeff's going to know behind, I don't think there is because of the number of passengers. Whether EASA decide that there might need to be, I don't know. The interesting bit that I was actually on the telemetry.
Sorry, it's right, the number of passengers. Is that the rule?
Yeah, it normally is now at the moment.
Is that why you're staying at 4 passengers?
No, that's not why we're saying 4 passengers. We're saying 4 passengers because actually, in terms of the technology, in terms of power density of batteries, a light aircraft is kind of where the technology is now to produce an aircraft that we could certify and get and produce and sell. Whether all electric, pure all electric can scale up to higher number of passengers, where in a sort of part 27, 29, you might need a flight data recorder. I'm not quite sure.
The certification rules have still been written for this kind of stuff.
Yeah, well, it's a case of whether, as EASA, right, for eVTOLs, particularly in the advanced air mobility market, whether they see the need to put flight data recorders on the aircraft or not is something that it's down to them to work through. I'm sure, obviously, we'd like not to have the wait. The other bit that I would point out on the telemetry bit, something that we're doing with our test aircraft that's being built now is obviously we're looking at through life and looking at big data, digital twins, and all that kind of aspects. and making sure that we know that if the aircraft lands and it's got a slight fault, we can fix that fault before it turns around and goes again. So this aircraft is going to be connected. So we're going to be streaming data off this aircraft all the time. So in terms of understanding what's happened to an aircraft from a flight data recorder perspective, actually in the cloud, we may already have that information provided. So whether we need a flight data recorder, I think is something that will have to be discussed through with the regulators as we go. But there will be data on the aircraft in the cloud all the time, because we're going to be looking at how the aircraft is performing, how its health of all its components, so that we can help make sure that our operators have the aircraft as available as they possibly can be.
Then it might be an issue with access of the data from the federal investigation.
Yes, and I have to say, I'm not the chief information officer, so I don't have to worry about that sort of stuff.
Sorry for that.
But no, but in terms of cybersecurity, all those aspects, those are things that we've got a whole IT and information team who are looking at all those various aspects of delivering the product through life.
It's another subject. Other questions?
I think we've got one or two at the back.
You talked about essentially 3 flight regimes, going up vertically, transition and forward flight. So how are you getting on with the authorities on sort of what I call worst case? Take an example, bird strike.
Yep.
Birds will always find you out and they'll always find the worst case, regardless of what you think you're doing. Have you got a sort of strategy of you'll demonstrate worst case and simulate the rest, or?
Yeah, we're talking around bird strike. We've actually brought in somebody from Rolls-Royce who's looked at bird strikes on turbofans and whatever. So there is a keen interest in how do we look at making sure we're appropriately tolerant for those rotors for bird strike, but equally, if the worst does happen, the whole part is actually building enough tolerance in the aircraft so that actually it should be able to take it. We say that, we look at the Hudson River incident where the twin engine just took a big flock of birds. Obviously, the other part for that is making sure the aircraft can still operate and get to the ground in a continued emergency landing at some point. So we are building up our CERT program of how many rotors do we have to destroy and how many birds do we have to throw at it to prove that it's appropriately robust. So it's an interesting area, and we've had some interesting ideas about how do we catch a blade and all that kind of stuff. We don't have any ducting around those blades, so try and make sure that the blades are positioned appropriately, that it's safe for the people on board, and we can take appropriate measures in the event, in the unlikely event, although it does happen, of a bird strike. So it's about trying to build up the tolerance or redundancy in the systems to allow us to tolerate that and react to that situation if it happens.
And on the authorities sort of thinking about different strategies for the different flight regime, because you can imagine as you're going up vertically and something happens, bird strike or anything else against going forward, you could have a different reaction to it, couldn't you?
Yeah, I mean, if you look at the ANSA special compliance, they've effectively just grandfathered over the category A aspects for helicopters. I'm not so keen on that. We've had our own internal discussions about that. The problem with doing that is that many of these aircraft are relying on rotor speed for their control in the heave axis. Whereas if you have an engine failure in a helicopter, you can start changing or exchanging energy between the rotor and your speed and your height at different times. And that's how category A has been set up. We will probably need to have something similar, but because there's very few of these aircraft out there, we just don't know a little bit. So we need to, this is a big thing I think about Vertical, is we like to build stuff and get it tested. I think once we start to fly the aircraft and get an understanding, and particularly put it in our simulator and start failing things, our pilot loop simulator will have a big dome, in a few weeks' time, and we'll be back in there and working through it. We will have to look at those takeoff and landing procedures, and the different takeoff speeds that you have in category A, I think might need to change, but they might also change depending on the type of concept and architecture you have for a particular eVTOL. So we might have to define them for each concept, potentially. So it's an interesting area. And we don't know the answers yet, I think. It's probably the main thing.
Question?
The one behind you. I'm conscious we're slightly over, but should we make this the last one?
That's fine.
Thanks very much for a very informative presentation. Andy Roberts from Rolls-Royce. Following on, I think, from the last gentleman's question, you're obviously doing a huge amount of learning through this program. at the same time, your regulator and your certification authority are also doing a huge amount of learning. How are you managing taking them on the journey with you? And how are you managing the challenges of effectively knowing that your certification specs that you're aiming towards are still being drafted while you're doing your flight test?
Yeah, so it's about getting an agreed means of compliance, really. So we are in, I wouldn't say day-to-day conversation, but we are in regular conversations. Initially, mainly, because we obviously want to fly a prototype aircraft with the CAA. So our airworthiness team are in constant dialogue with the CAA. I think it's reflected by Simon Harper, who's our head of test on the panel yesterday. Yeah, we have a number of our key people who are helping to inform various EUROCAI working groups as well. In fact, our battery lead is actually leading that working group. So it's about us engaging with the regulators so that as we are learning, they're learning as well. So that helps so that we understand where the regulation is going to be and help to inform it to make sure that it's appropriate for what we're trying to achieve. Very much with the example that I gave with the battery testing. That battery testing has been going on for probably 2 or 3 years, and EASA and CA have been along for the ride on that. So they have seen firsthand all of those tests of fire ripping through and how long that takes, and working with us and talking to us about how we develop a battery system that is airworthy for what we're trying to achieve. Thanks, Andy.
Any additional question?
It's gone quiet. They want coffee.
Congratulations.
Thank you.